Hello, we're Group 80 and we're excited to share our project MyoSense. In this project, we worked to develop a gated convolutional neural network for classifying hand and finger gestures using surface electromyography, or EMG. It's a cool intersection of machine learning and biomedical engineering, which we all have backgrounds in. Now, as a quick introduction to our topic, EMG signals provide a valuable means of understanding motor control. These signals can be used in prosthetics development, rehabilitation, and human-computer interaction to help individuals who can generate electrical signals but may have lost limbs and are unable to actuate it. The signals can be used to determine intent of action. Our goal here is to figure out what someone intends to do based on these muscle signals, possibly later integrating it into an assistive device. Now, traditionally, controlling a prosthetic or interpreting EMG involves some heavy signal processing and simple classifiers. The problem is EMG is messy. It's high-dimensional and noisy. These traditional methods often fall short when it comes to real-time processing or understanding complex motions. That's where machine learning comes in. It can help us extract useful patterns and make better, faster predictions of intended motion. For our data source, we based our model on the NinaPro DB2 dataset, a widely used benchmark for hand gesture recognition. It includes surface EMG recordings from 40 participants with intact limbs, collected using 12 electrodes placed strategically across the forearm and hand. These recordings correspond to 50 unique hand gestures that range from basic movements to more complex combinations. However, to keep the scope manageable and reduce class imbalance, we selected a representative subset of 6 gestures. These are shown on the right side of this slide. These were chosen to reflect a diverse range of muscle activations, including flexion, extension, and abduction. Each gesture trial is accompanied by precise ground truth labels and kinematic data, which made this dataset ideal for training both a baseline and a deep learning model. The process starts with raw EMG signals and gesture labels. For our baseline model, we use time domain features to work with a random forest. However, with our CNN model, we pre-process the data into spectrograms, using a sliding window of 200 milliseconds with a 100 millisecond overlap. These spectrograms became the input for our CNN model, which then gave an output of the predicted gesture labels. For an overview of the model, our CNN architecture starts with 3 convolutional layers with increasing depth, 64, 128, and 256 channels, each using 3 by 3 kernels. These are followed by a flattening step and a fully connected layer. We applied ReLU activations, 2 by 1 max pooling, and a dropout throughout to prevent overfitting. To improve performance, we added class weights to balance underrepresented gestures such as 3 and 4. We used early stopping and optimized parameters like learning rate and batch size with using Optuna. We also experimented with data augmentation techniques to address class imbalances. For evaluation, we used a participant-independent testing strategy, meaning that the test set included data from participants completely unseen during training. This is more realistic assessment of model generalization, as EMG patterns can vary widely between individuals. We evaluated performance using standard classification metrics such as precision, which measures how accurate our positive predictions were, recall, which captures how many relevant instances we correctly identified, and the F1 score, which balances both. We also used a confusion matrix to visualize where the model made the most mistakes. This helped us identify specific gesture pairs that were frequently confused, such as ring/little flexion being misclassified as index/middle extension. For our results, our CNN outperformed the random forest baseline across all metrics, particularly in F1 score, improving from 0.22 to 0.37. The confusion matrix highlights that the model struggled most with classes 3 and 4, likely due to overlapping muscle activity patterns. While building and training the model, we tried many different avenues for optimization. However, all improvements capped out around 40% precision. In summary, our CNN model showed meaningful improvement over the random forest baseline, particularly in F1 score. However, the model struggled with specific gesture classes, especially class 3 and 4. These difficulties likely stem from overlapping muscle activation patterns, For example, in ring/little finger flexion was often misclassified as index/middle extension, possibly because both gestures involve activation of the middle and index finger muscles. This highlights one of the main challenges of using EMG. The spatial proximity of muscle groups can lead to signal similarity. To improve classification, future work could explore adding more temporal context using LSTMs or modifying the pre-processing pipeline, such as reducing spectrogram dimensionality with PCA or experimenting with alternative window lengths. No prior work was done on this project, and these are the references we used. Thank you so much for listening, and have a good day.